Okay, it's time to bring some new data types into the mix. So up until now, we have primarily been dealing with lists, and we will still look at lists for quite a bit. But in order to make things more interesting, we're going to introduce some new data types and see how we can define functions that make some use of these data types as well. And the first new data type we're going to look at is pairs of two elements, or more generally speaking, even tuples, although I must say that apart from pairs, tuples are relatively rarely used in Haskell. So one way to look at a list is that it is a collection of arbitrarily many elements of a particular type, right? And we don't know exactly how many elements we have. So that is determined only at runtime. The type of lists allows us to have a list of 3 elements just as much as a list of 300 elements, right? It is, both are of the same type. On the other hand, for a pair, we know that we have a collection of exactly 2 items. At the same time, we can make both their types precise and they can have different types in principle. So both the types of their things are known. So a pair is just a collection of 2 things that are possibly different. Pairs are, and tuples in general, are once again an example of a data type that has special syntactic support in Haskell. So we cannot reproduce the definition of tuples exactly in our own modules, but just as we had been defining our own version of lists, right, we can also define our own version of pairs. And I actually want to start by that. I want to demonstrate how we would be able to give our own data type that is essentially defining pairs as well. That is exactly equivalent to the built-in notion of pairs, except for the additional magical syntax that we are able to use there. So a pair now is a data type that is parameterized, just like lists were parameterized, but a pair actually has 2 type parameters because we have 2 components of the pair. So we write data pair AB. And another interesting feature of pairs is that there is only one constructor. So far we have mostly seen data types with 2 constructors. In principle, they can have arbitrarily many constructors, but Booleans, for example, they had 2 constructors, false and true. Lists had 2 constructors, one for the empty list and one for cons. And choice was a data type that we've seen in the very beginning, this rock, paper, scissors data type. That was a data type that had 3 constructors, namely rock, paper, and scissors. So here we have only one constructor, and we have a free choice how to call this. So we could call it, for example, make pair or something like that. But actually, Haskell is allowing us to use the same name for the constructor as we use for the type. That can be done in general because types are living in a different world from constructors. Constructors are part of the expression and the pattern language. Types are only appearing in type annotations and type signatures. So these are different places in your program. So it is always contextually clear whether you're talking about a type or whether you're talking about a term, like an expression or a pattern. And therefore, the same name can be reused, and it is always contextually clear which of the 2 things we mean. And because Haskell does this quite a bit, we are going to do this as well, right? Remember that we had already said that, for example, the notation, a list with just a 2 in it, that is a single element list if it appears on the term level, but then square brackets with int in it is not a single element list. It is the type of lists of integers. So this kind of reuse of notation is common in Haskell. So we're going to use this here as well. So we're going to reuse pair as the constructor, as the only constructor for pairs. And the pair constructor, again, has 2 arguments, one of type A and one of type B. What this definition now means is that we can form a pair by applying the pair constructor. So if I ask what is the type of the pair constructor, it takes an A and it takes a B and it collects them into a pair. I can do this with arbitrary things. So I can take the character X and the Boolean true and form a pair out of them. Of course, if I'm now just hitting return here, I'm getting my typical error again that pair at the moment is not an instance of the show class. So it says actually it infers the type of the expression that I've written to be a pair of a character and a bool. And here the pair is the type pair, right? So because X is a character and true is a Boolean, but then it says that there is no show instance for this. But I can actually say deriving show as usual, and then it will actually work, right? So I can then get the pair printed back, and of course I could also just have asked for the type of it, and that would print this back. And again, you see the two occurrences of pair here. Pair on the left-hand side of the colon is the constructor pair. Pair on the right-hand side of the colon is the type pair. If I had used make pair here, as I originally suggested, that would become more obvious. Then I would have to write make pair here, and then I would see that make pair is the constructor and pair is the type. Okay. And that's it. That's our definition of pairs, right? So there is only a single constructor, and that collects these two things. Now, there are not all that many interesting functions we can write with pairs in isolation. So, one function that we can write is one to extract the first component of a pair, and this is one that is predefined again, so I should do the usual hiding trick. And I'm going to write this for our pairs at first. So the idea is to extract the A out of a pair of A's and B's. And we can use our general pattern. We have started with the type signature. I'm introducing a name for the argument. Let's just call it pair. And just as usual, the only thing we can really do with a new data type is pattern matching. The most fundamental thing we can do is pattern matching, right? And usually, again, we had data types with multiple constructors, and we have been perhaps seeing pattern matching primarily as a way to distinguish cases. But pattern matching really has two combined purposes: to distinguish cases and to get access to the components, to the arguments of the constructors, right? In the cons case for functions that operate on lists, we also get access to the head and the tail. And for pairs, pattern matching does not introduce multiple cases because there is only one possible constructor to choose from, but it is still giving us access to the two components. So I can write pair, and then I can give names. I could actually use A and B here as well, but I'm going to just call them X and Y. And then if we look at the whole error message here on the right, we now see we have to produce something of type A because that's what the type signature says. And we get nicely listed here that our relevant bindings that we have locally in scope, in particular, we have X, which is of type A, that is the first component of the pair, and Y, which is of type B. So now I can just write X in order to get the first component out, and I can write an underscore for the Y because that I actually want to discard. Okay. Now, first is a totally safe function, and because it is total, a pair always has a first component. This is different to some other extraction functions that are actually in Haskell, but that are more problematic. So, for example, there is a function head that some of you may know if you have background from either Haskell already or from other functional languages or Haskell-like languages such as SML or Camel or PureScript. there is a function head that selects the first element out of a non-empty list, but a list does not always have a first element. If we call head with the empty list, we get a crash, we get an exception, and that is bad. Like partial functions, so-called partial functions that can loop or functions that can crash, are strongly discouraged in Haskell, because these exceptions, they're tricky to deal with. And so in general, calling head is not a good idea. I would actually be happier if head was not even available in the prelude. It can be defined somewhere, but it should not be exposed as prominently to the user as it currently is. First, on the other hand, is a safe extraction function because a pair always has a first component. Nevertheless, pattern matching on a pair is so easy that in many cases it is actually still more convenient and more readable to write a function using pattern matching rather than by calling first and second, I would say. Another thing to say is that because pairs have only a single constructor, we can actually also use pattern matching in a lambda for a pair. So what we can do is, if we wanted to extract the first component of a pair anonymously, we could just write, take a function that takes a pair of an x and something and then returns the x. This is a way to anonymously define the first function. And if I apply this to, now I've gone ahead and used the built-in syntax. We could have used pair x underscore, okay? And if I apply this to a pair and x and true, I have not reloaded here since making this renaming between make pair and pair, then it will correctly extract the character here. Perhaps it's not a good idea to call the variable x and then use it on something that is looking almost the same. So if I take a different pair here of a boolean and a list or a string, then it extracts the first component. This sort of pattern matching in a lambda is not useful for data types that have multiple constructors, right? Because we cannot actually distinguish several cases here. For that, we need a case expression or a function definition that can have multiple equations. But if a data type has only one constructor, then there is only one possible choice, and then it's okay, and this can be used. Okay. So now let's combine this, or compare this to the built-in notion of pairs. So the pairs that I have just written, character x and true and false and string foo, in the built-in notation they would be written like this. So we form a pair by surrounding it with parentheses and separating the elements with commas. Right, so round parentheses are tuples in general. Square brackets are lists, right? And as a list, this would not work because we have two elements of different types, a character and a boolean. We would get an error message that says essentially this. We cannot put these into a list together, but we can form a pair out of them. So the pair constructor, or what was called pair for us, is essentially this combination of the two parentheses and the comma. They together, they are the syntax for forming a pair. And actually, they're also the syntax for the type of pairs, just as we are using the same name here for the constructor and for the type. If I'm asking what is the type of this pair, I'm actually getting this syntax here for the pair type as well. It's a pair of a character and a boolean. If we use this magic I command, the info command, to get information about the pair type, we have to know how to write the pair type in isolation without applying it to its arguments. And just like there is this way of writing the list type without its argument by just writing square bracket open, square bracket close, right? So that gives us this data type definition that we could not write ourselves for the list type. There is also a way to write the pair type without applying it to its arguments by just writing the three symbols, parent open, comma, parent close, next to each other. And then we'll get some data type definition for pairs that, again, we could not have written ourselves because this syntax here is simply not available for user-defined types. But we can see that it has exactly the same structure as the pair definition that we have been giving. So the type has two arguments, A and B, and the constructor has two arguments, A and B. And actually, this prefix notation is available, even though it is completely unidiomatic, but you could form a pair of the character X and the Boolean true by prefixing it, but then it's still printed back to you in this more readable and much more common way. Okay. Just like there are pairs, there are other tuple types in Haskell as well. So there are triples, quadruples, pentuples. So we can basically make a collection of various different things if we want. So let's do here pair up 4 different things, right? So that works. If we ask what is the type of this, then we get it follows the same principle. We get that this is a tuple of 4 components. The first component is a character. The second component is a Boolean. That's the false. The third component is actually any numeric type. Right, because we put an integer literal here. And the fourth component is a list of Booleans, right? So you can mix and nest types arbitrarily. You can have lists of pairs or pairs of lists and so on and so forth. And functions can be part of all these as well. So I could say I want to have a tuple which has the first component contains the plus function, and as the second component contains the take function. And then we'll get a very complicated type signature, but again, plus is an operator that goes from something to something to something, all for the same thing, and it has to be in the num class, and take is a function that takes an int as the first argument and then takes a list of something which can be something else than the thing that the plus operates on. So that's why it gets a different type variable and then produces another list of the same way. So you can get very complicated types with very simple means already. That doesn't mean that they're necessarily used a lot in practice, but the system that you have available is very flexible. One often useful function that's perhaps fine to introduce. Perhaps I should redefine the first function now on the built-in pairs ones, just to make clear that pattern matching then also works in the same way, right? So just in the same way as before, we have written pattern match on on our own pair constructor. We could now define this like this. And sorry, I should of course then also use the built-in pairs as a type signature, right? Even though these two data types are structurally the same, our pairs that we've defined here and the pairs that are built into the language, I cannot, of course, use the pair constructor that I have defined for the built-in pair type and vice versa. They're structurally the same, but they're still treated as completely different. Every new data type declaration in Haskell introduces a completely new data type that is considered to be distinct from all the other data types that exist up to that point. And often we use the type system specifically to make distinctions between things that are structurally otherwise very close or even equivalent, right? So it's very important to say distinguish email addresses from phone numbers, even though we might use a string as an underlying type to represent both of them, right? So different conceptual notions, even though they're structurally perhaps represented as the same way, are often supposed to be kept apart. And in Haskell, if we define a new data type, then it is different from anything else. But the notion of pattern matching works in exactly the same way. There's one other function that I want to briefly discuss using pairs, and that is the function uncurry. It is sometimes a useful function because most functions in Haskell are curried, as we've said. In principle now, we can also define functions that have two arguments as taking a pair of things. So, for example, I could write my own addition function on a pair of integers like this, and I could say, if I have a pair of integers, yeah, pattern matching again, I just call x plus y, okay? And then I can, just like I could have called the original plus, I could also call plus with a pair of two integers. In general, every curried function of two arguments can be turned into a function that operates on a pair. And this general notion is what the uncurry function captures. It says exactly this. Sorry for it. Uncurry has the following type. It takes a function that expects itself two arguments in curried form. So the general form of a two-argument function in curried style is a to b to c, right? So it takes an argument, it takes another argument, and it has a result. Any two-argument functions fits into this pattern. And it turns this two-argument function in curried style into a function that expects a pair of two arguments. So into a function that expects a pair of an AB and turns that pair into a C. I should hide uncurry again because that also exists. Okay. Now, we said the function arrow is right associative. All right, so if these parentheses here, they're actually not needed. Whether I see this as a function of two arguments, one that like expecting a binary curried function and then a pair and then turning that into a result of type C, or whether I see it as a unary function that expects this curried binary function and then returns a function that expects a pair and turns it into a C, that is equivalent. Right? And for defining it, the view without the extra parentheses is easier because then we can just introduce two arguments. We get this function f, and we get this pair, and then we have a whole, right? And now we can use pattern matching on the pair as usual. So I get the x and the y. X is of type A and y is of type B. And f expects x and y, but in curried form. So I simply apply f to x and then y in order to get something of type C out. I mean, here the whole is perhaps really informative. So we have to produce something of type C, right? And what do we have available? We have f of type A to B to C, and we have x of type A, and we have y of type B. And there is basically no other way of putting them together than applying f to x and then y, right? So that is the obvious choice here. And if we have uncurry, right, we could have been writing plus as a special case of an application of uncurry. Namely, we could have just said plus is uncurry of plus. So actually, I mean, perhaps one step more. Right, if we have a pair of x and y, then we could call uncurry on the plus function, turn plus into a function that rather than expecting its two arguments separately in curried form, as plus does, right? Plus operator is a to a to a, so it fits this pattern. So uncurry of plus is now expecting both its arguments as a pair. So we can feed the pair that we got to that. But now the pattern match is actually unnecessary. We don't even need the pattern match anymore. We can just take the pair and then pass it to uncurry. And even picking up the argument and passing it on is unnecessary, because if we look at the partial application of uncurry to plus, this is the right type. This is a function that expects a pair and produces a result. And in particular, if we instantiate c to int, it has exactly the right type. We can convince ourselves that this works. Plus of the pair 3, 5 is 8. Okay. I guess we'll see uncurry in action in a few places later on. As I said, sometimes if you're working with pairs, uncurry is useful because most functions, right? Most functions that we have available in Haskell, most operators and so on and so forth, they're all in curried form. So if we are working with pairs all of a sudden, we may sometimes want to apply both components of the pair as arguments to a function, and then being able to uncurry the function is sometimes a useful operation to have. Okay, that's enough as an introduction for pairs. Next, we're going to look at how we can use lists of pairs as a not very efficient, but relatively simple to construct representation of so-called dictionaries or lookup tables.